Thank you very much, and thanks everyone for having me. So, I guess a brief intro to me. So, oh gosh, this mic is, sorry, sounds strange to me. So yeah, my name's Nick. I currently work at Tweak.io, and this talk's going to be a little bit about some of the work that we've done there. But before I talk about more modern work, I'm going to jump back a few years. So, I used to work at the Wellcome Trust Sanger Institute, which is a genetics research institute outside Cambridge, and it's extremely pretty. And I should emphasize that when I say how to fail at science, this is not in any way them failing at science. It's largely stories of me failing at science, despite their best effort. But it's also about some of the ways in which some of the analysis that we did often went wrong. And it's going to be a little bit about some tools that we've later developed and how they can help with those problems. So yeah, mostly what I did there was working in sort of tool support for the human genetics faculty. But occasionally, when they were feeling particularly foolish, they would let me do some analysis by myself. And so what are some of the things that would happen? Well, so this is a standard, this is a standard sort of set of steps for doing something called variant calling. And it doesn't really matter for the purposes of this talk what variant calling is. But you can see you would start off with, a file called my.faster, which was something that had actually been read by a genome sequencing machine. And so you would do something to align that to a particular reference genome, and that would get you out one file. And then you would, I can't even remember what you would do to that, but you would follow a set of steps that somebody had written down somewhere. And after following about 10 of these steps, assuming they all went right, you would get some output. And then you would realize that, oh, actually, no, sorry, this output's invalid. I needed a 3 rather than a 5 up in step 2. So you'd go through and you change that to a 3, and you generate a new output file, and then you diligently trace through and work out where that new output went. And you'd follow this through, and then you'd realize, oh, hold on. Actually, this is a new version of that piece of software. I need to cut out fields 1 to 9 to make this work. So you'd go back and you'd cut out fields 1 to 9. And, and then you'd get a different slide. And you'd basically keep going on, doing this, and so on and so on. And then a few hours later, finally, you're like, yes, this is exactly the file that I wanted. These are the results that I wanted to get. And then you'd wonder, so how did I get that again? And you'd spend another few hours traipsing through your bash history and working out which commands worked and which ones actually produced the output that you wanted. So I'm going to call this the provenance problem. I have produced some results. Where did they come from? So the second problem, and this is the one that really sort of comes up in the talk title, and it's the one that gets a lot of attention, is, well, I've done some analysis over here in the UK. And when I say analysis, I'm often talking like, yes, this is computational in silico analysis. This is, I've done an experiment given this file, and I've got these results. So now I have some collaborators over in India, and I want to take my analysis, I want to box it up, I want to send it over to India, and I want them to be able to run that same analysis and hopefully get the same results, or at least get different results, and that tells us something as well. And this is the reproducibility problem. I've done something, I want other people to be able to reproduce it, I want to be able to reproduce it 6 months in the future, even though sort of my cluster has changed and I maybe don't have some of the intermediate data around. And problem 3, which is closely related to the sort of the reproducibility problem, but this was one that came up quite a lot. So you're working on a shared cluster, and you run your analysis, and you're halfway through running your analysis, and somebody somewhere else in a different building decides they need a new version of a particular piece of software they're working on. So they email the administrators, and the administrators are like, okay, yeah, we need to update that, and ultimately you end up updating glibc. And you go to run your analysis, and you're like, this is interesting. I'm getting slightly different results to what I got last week, but I'm doing everything exactly the same. Because the problem is, the analysis that you're doing is not isolated from everything else that's happening on the same cluster. And this was a big problem, and this caused, lots of difficulties for the teams that we were working with. So this is, call this the isolation problem, that your software isn't isolated from everything else. Okay, so that's the background. What is this talk actually about? Well, it's mostly going to be a talk about workflow systems, what they are, how they can be used to address the kind of problems that we've talked about. And in particular, I'm going to talk about a workflow system that we built last year that is hopefully slightly different from existing workflow systems in potentially non-trivial ways, and how we've applied that to some of these problems. And sort of, more in general, how I think we could apply it to the sort of problems that I've just discussed, and maybe some other things that haven't been discussed but sort of I've thought about in the future. But actually, before I do that, I'm going to start with an interlude. So, the problems that I was talking about, this was back in 2013. And an obvious question is, well, we identified a bunch of these problems at the time. Did we try to do anything about them? Did we try to address these? And the answer is yes. And so we thought, well, we found these various problems. We've written up a big report trying to work out what we should look at. What's the first problem to tackle? And we thought that a sensible first problem to tackle would be the isolation one of like having your computations isolated. So if you remember in 2013, there was this feature called LXC, which was just starting to get nicely stable in the kernel. Just indication, does everyone know roughly what LXC is? I don't know whether hands were I don't know or I do know. Hands for I don't know. Okay. So LXC is a kernel feature that basically lets you do sort of kernel namespacing. So in particular, it lets you have isolated containers, and they have their own process namespace. They have their own basically memory isolation. They have their own user namespacing. So they're as isolated as one can get without being virtualized. So we thought, what we really need is an easy way to be able to deploy and manage these containers. So the timeline looked a little bit like this. So we started sort of February 2013 working on this tool called HGC deploy, which was actually written in a camel. And this was a tool for managing containers running under LXC, and it used some union file systems and things like that. And a month later, someone happened to flag up there was this company nobody had ever heard of called .cloud, and they announced this thing called Docker, and we had a look at it, and it had about 5 developers. So for those of you that went to Abby's talk this morning, I felt very guilty sitting there because she was talking about the culture of contempt and how we as Haskell programmers can often just sort of straight away dismiss other programming languages as if that's something to do. And I thought to this slide, because I'm afraid that one of the things that we saw was, oh, this tool's written in Go. Clearly, it's not even worth looking at. And maybe I should feel guilty about that, but I can at least relate that was the experience back at the time. So we looked at this and thought, yeah, that's not going anywhere. And I mean, I think you're way ahead of me. August 2013. We've sort of been gradually watching this and we're like, yeah, okay, they've now got about 50 developers and they've got something like 3,000 commits. And the end of this story is it turns out we did not end up taking over the world with our camel-based container management system. And this little thing called Docker somewhat beat us to the post. I like that. I like to have hopefully got the first sympathy groan of the conference here. Okay. So let's roll forward to 2017 and hopefully less traumatic events. So I want to talk about workflow systems. What are they, and how are they interesting? So a workflow system is basically a way of assembling a program through composition of smaller programs. And most of you are probably thinking, yes, that's you're describing programming there, Nick. That's how we generally work. So, and it really is effectively that. But the idea is, this is very explicit composition. It's often like drag and drop programming. You're taking, oh, I have a box that does X. I'm going to connect it to a box that does Y. I build this into a composed program. So they look like flow diagrams. And I say I'm going to probably use the terms workflow and pipeline and flow fairly interchangeably here. So a sort of straightforward example of this, for those of you that are familiar with MapReduce, you can sort of see that as being a workflow in here. You start off with some documents, and then you have your map step where you map over the terms in those, and then you have sort of your shuffle step, and you get the outputs from the shuffle step, and then you've got your reduce step that actually gives you the outputs. And there are a very large number of workflow systems out there. They have a long history, particularly in things like business process management, where you'll have gigantic systems where you can sort of annotate all of your workflow steps in WSDL and connect them together, and you deploy giant servers run by Oracle, and they will, make sure that your email gets sent out on Tuesdays. Or potentially some things more interesting than that. But they also have some background in scientific processing. And our experience is that in scientific processing, they're somewhat less intelligent, and they're somewhat less advanced. But there still is the question of, well, why go about writing your own workflow system? And with apologies to Randall Munroe, it was basically this. So, we were standing there looking and thought, oh, there's about 100 different workflow systems. I was like, God, it would be quicker to just write our own than it would be to search through 100 different systems and see if any of them actually satisfy our needs. I was like, yeah, that sounds more fun. A few months later, there are 101 different.
What's the difference between a workflow system and a build system?
That is a good question. So, I mean, they're very similar. And I would say that effectively a build system is a workflow system with like a graph composition step in front of it. So in a workflow system, going back, say here, you effectively start with the graph of your workflow. And what you don't particularly care, I mean, this is potentially a bad example because what I've actually displayed here are the outputs. But often, you don't care about the intermediate outputs. You don't name them, you don't label them. You're pretty much writing in a point-free style where you are, you're not labeling things, you're just composing these steps. A build system typically, I think, will ultimately resolve to a workflow system, but the first thing you do is you say, well, I have, this step here that depends on this. And you say, oh, and I've got this thing here which depends on this. And the first thing that the build system does is it goes, oh, I've got this whole load of outputs. I need to go through here, and I need to basically order them in such a way that I do the first steps, and then I do the next ones, and then I do this until I get the output. There's some, I think there's also some differences in sort of how they're used. So, so workflow systems, I think, potentially often more have a focus on being distributed and being able to spin things out in other places. But they're really very similar concepts, except that typically workflows, you start with the graph and you don't really care about what the intermediate outputs are. So for those of you that have read Simon and Neil and on the build systems paper, I don't know whether, sorry? Okay. They talk about one of the things is can build systems have dynamic dependencies? And there's a thing of, well, so for workflow systems, can they have dynamic dependencies? And so at least in the one I'm going to talk about, the answer is, well, kind of. It depends on how you think of it, because what does a dynamic dependency mean in a build system? Well, often it means I don't know which files are going to be produced, and I want to kind of depend on whichever files get produced in some way. In a workflow system, you don't care what files get produced. You just care about it's the output of whatever this step is. So in that sense, you can have dynamic dependencies. What you can't necessarily have are saying, the structure of my graph is going to rewrite itself depending on certain steps. I mean, you could obviously have a workflow system that did that, and some do. Does that answer your question? Okay. So yeah, anyway. We ended, and the result being there are now 101 different workflow systems. These numbers may not be accurate. So what do we build? Well, we built this thing called FunFlow, which is a workflow system built around arrows. One of the things that we really wanted was to be able to sort of closely integrate things that were written in Haskell with external tools. So often with a workflow system, what you're doing is that you are composing, I've got this Python step here, and then I've got this bash script, and then I've got, a call to a web service, and I want to chain them all together. It's kind of a if this, then that style composition. And we also wanted to be able to just say, well, actually, I've got a Haskell program, which a substep of that is to go away and run this workflow somewhere. And I want to treat that as if it's just any standard Haskell computation. And probably the more interesting thing is using like a Nix-style store, except an intentional store, so a content address store, and I'll talk about what that is. And then, you know, using containers for isolation of steps and sort of allowing distribution of stuff. So on to the first point. So, you know, what's an arrow? So this is something that was introduced by John Hughes in 1998 in a paper, and so this is a quote from the arrows page on the Haskell.org thing. The only reason I include it on this slide is because every time I read this sentence, I assume that it's meant to be read in the style of the A-team thing. So it's like, if you're using a structure, it's very like a monad, but it isn't a monad, then maybe, just maybe, it's an arrow. But that might just be me, and I'll apologize for that. So what is an arrow? You know, so we can ignore the category thing pretty much. I think of them as basically generalizations of functions. You know, a function is something that takes an A and returns a B. An arrow is something that, like, you know, has an A on one side and a B on the other side, and it's not, you know, clear. It doesn't necessarily take something. You know, it just really is an arrow drawn from A to B. And, you know, you can use these. These are a nice fit for sort of workflows, because, you know, one of the things you can do with them is that you can compose them. So if I have an arrow from A to B and an arrow from B to C, then I can get an arrow from A to C. And you can sort of see that these, you know, these sort of box diagrams look very much like the workflows earlier. So you can lift a function into an arrow. Yeah, you can compose them. And they have this other operation that's sort of, you know, called first, which basically says if I have a tuple, I can send one component of it through the arrow and keep the other component unchanged. I have no idea. No. So these are kind of interesting because they generalize a lot of the stuff that we sort of really think about our computations in. So, you know, functions are an instance of this. I can very easily define the arrow instance for a function, but also monadic functions. And these are the so-called Kleisli arrows of a monad. So given a monad, if I have a function a to mb, then that itself is an arrow. And also other things like, you know, so stream transformers are one of the things mentioned in the original paper. External computations is, you know, so this is saying, this is sort of a concept similar to us, is saying, well, if we've got a Python program somewhere and that takes in, you know, a BAM file and it outputs, you know, a picture of a cat, then, well, this is a viable arrow from BAM files to pictures of cats. So this generalizes a lot of the things that we care about. And in particular, it lets us say, well, now I have a concept in which I can generalize Haskell computations and monadic actions and, you know, external tools and other things that we might choose to use. I guess one of the things that currently cannot be an arrow are linear functions. But I guess that's only up to adding another parameter in the arrow type to give the, can I go backwards? Yeah. We'd have to add another parameter in the arrow type to give the multiplicity kind here, for those of you that were in Simon's talk this morning. And the other thing about arrows is that they actually have special syntactic support in Haskell. And this is, by all accounts, a bit of a wart. And when I say a bit of a wart, it's, by all accounts, a lot of a wart. And one of the really hairy parts of the Haskell compiler that a few people have tried to make better over the years and generally failed. But they do have this special support, so you can write something very like do notation for these. There's a proc keyword, and the arrow syntax looks very much like you are just feeding things into these boxes, except it goes, you know, right to left rather than left to right. So I feed X into the F arrow, and I get Y out, and I feed X into the G arrow and get Z out. And then there's this return A. This isn't the keyword actually. Oh, no, it is a keyword. Return A, which then just gives me the result of these, and that itself is an arrow. So There we go, we're fine. And GH is not actually brilliant at this compilation process. So, you know, there are things which could compile into, you know, so we've got this sort of parallelism concept here. You know, we've got that we can split things apart. And Haskell, GHE won't in general compile, you know, if I take something like this here, so you can see that actually I should be able to run F and G completely independently. Actually, this will be compiled into a sequential operation, so it means you don't, you know, get everything that you'd like.
But if you use the arrow P processor from HaskellX, then you get nice.
Okay.
code.
I'd heard that there are libraries, but I've never. That's a template Haskell.
There's one which is a template Haskell, and then there's the original one by Ross, which is just using Haskell X or Haskell source.
Okay.
Those produce good code.
Okay.
Yes, it does.
I should have a look. So, you know, how do we use this? Well, yeah, we want to integrate sort of different types of computation. And so we have this sort of arrow, you know, like MTR style arrow class, you know, where we have constructors for different types of things. So you know, you have pure functions, and there's some extra stuff, you know, that you can annotate them with. Or we have I/O actions, or we have some kind of external task, you know, or we have this wrap thing which says, well, a user can define basically their own algebra of effects. So we have a notion of effects, and those effects are sort of themselves arrows, and we can lift those into the computation. And so the second thing, and probably the most interesting thing, this will come back in a second. The second thing I want to talk about is, you know, the use of basically a Nix-style intentional store. So what does that mean? So one of the key things, going back to like the reproducibility, the provenance example from the start, is that when users can just write wherever they want, everything gets confused. And the correct answer to this seems to be, don't let users write wherever they want. You know, take away, in much the same way that sort of in programming, you know, and in Haskell we've moved from, you know, explicit memory allocate to this byte somewhere. We've moved away from that to, well, I'm just going to give this a label and let something else decide where to put it and decide when it's needed and decide when I can throw it away. You know, but with file systems, we're still largely dealing in structures of, I want to write precisely this to something labeled, you know, mycatpictures.txt. I don't know why we're writing cat pictures to a text file, but that's a separate question. Is most people familiar with Nix here? Again, okay, let's say no. So Nix is a package manager / system configuration utility that basically the key concept behind it is that your package is, sorry, I just had a panic because I looked at that clock and I thought I was massively early, and it turns out that clock is just wrong. So Nix, each package is basically controlled by a derivation. And what's a derivation? Well, it's an expression that tells you exactly how to build that package. And when you build that package, where does it get stored? Well, again, rather than writing sort of into the standard Unix-style file system, everything in Nix gets written into the Nix store. And it gets written into a path that is determined by the hash of every input to that derivation. So if I have, you know, my library funflow, and that depends on a bunch of other Haskell libraries, and it depends on GHC, and GHC depends on, you know, glibc, and depends on, you know, all the way up the stack, then the location of my package will ultimately be determined by the hash of sort of the closure of its dependencies. So what does that mean? Well, you know, for sort of an operating system, it means things like, well, I can have multiple versions of the same package installed all at once, and that's absolutely fine because they all get sort of namespace sensibly. And for a workflow system, what does it mean? Well, it means that if I have the same inputs, then I already know where the output is going to be stored. So, you know, I have inputs A, B, and C. Actually, I'm going to jump to few slides ahead. You know, if I have these three inputs, I can determine the path of the output. And so if I get those inputs again, you know, I don't need to bother reproducing the computation. I've already done it. I can just go and look it up in the output. So Nix has this concept that it's, you know, the hash of the output is determined by the hash of its inputs. We want to go sort of one step further. So one of the problems with Nix is that, you know, if you say, you know, slightly modify an upstream library, and it turns out that that modification to an upstream library, all you've done was add a comment. You know, it doesn't actually cause anything that depends on that to change. In the Nix world, unfortunately, that will cause everything downstream of that to be reevaluated, and the hashes will all change. So if you go and modify glibc to update a date or something, update a copyright year, you'll force the entire rest of the system to be rebuilt and reevaluated. But there's another concept called an intentional store or a content address store, and this is a very similar thing that says, well, when I store some data, where should I store it? I'll store it under its own hash. So I have a file f, I hash that, I store it under that path. What does that mean? Well, that means that if somebody else gives me another copy of f, I hash it and I say, yep, got that already. I don't need to store that. And so in FunFlow, when we run a task, we first store it and the hash of its inputs. And then when it's done, we hash the outputs and say, now we're going to move the results to the output directory and we'll link the input. So we have this idea of a content hashable class, which is, you know, you'll notice it's very similar to like the hashable thing, except that we've got this monad here. Because when we take the hash of, say, a file, if we have a file name, the hash of that is the hash of the contents of the file. So we're actually sort of doing a deep hashing here to make sure that we've captured the inputs. And then, yeah, so when we've got this sort of, with f, we've applied these inputs, we get an output path. We link that into the hash of the outputs down here. And the benefit of that is that, yes, if somebody now comes along and says, well, actually, I've got these other two inputs in this process G, if it turns out that that produces the same output, we both store it once and we store the metadata that says, I know that I can produce this output given both of these processes. So the idea here being that, you know, if, you know, again, looking back to some of the sort of the work that I did many years ago, you would often find that basically people would do very slight permutations that would actually arrive at pretty much the, you know, exactly the same results. And when you arrive at the same results, you know that you don't need to do all of the downstream computation again. You know, if I go and modify my -o parameter and I set it to 5 rather than 3, and it turns out that that actually didn't affect anything whatsoever, well, now I have a record that it doesn't matter which parameter I choose, and I also know that I don't need to go and rerun everything downstream. So the actual example that we were using this for was sort of on low-dimensional representations of data. So this is a technique from machine learning. Basically, you have some very high-dimensional data set, and you want to try to understand it, but understanding things in very large numbers of dimensions is difficult. You know, hard to process, and often you've just got sort of, you get the commercial dimensionality, so you've got too many dimensions than data points. So one of the things you can try to do is say, well, can I explain the interesting stuff in this data set in a smaller number of dimensions? And there's a bunch of techniques to doing this. And in our case, in particular, we wanted to try something which was, we'll say if we've got a very large data set, can we learn the structure of the data in terms of, you know, a lower dimensional subspace of that from that large data set, and then can we take a small data set that's of roughly the same structure and project it onto that lower dimensional space to try to explore that small data set, even though in itself we don't have enough data to sort of learn that structure. So this is just sort of a standard example. You know, I've got this high dimensional thing, and if I project it down onto the 2 dimensions, I can see that sort of most of the variance in these 2 dimensions just follows this arc. So actually, even though this seems to be highly dimensional, most of the interesting stuff is explained in a lower number of dimensions. And the particular constraints in this were, well, when we're training model, i.e. when we're taking this big data set and trying to learn the subspace, this is a long-running operation. It takes a few hours. And we want to be able to sort of avoid the problem where we've sort of trained a model. We want to keep that attached to the data set it was built from. And so one way of doing this is, well, say, the training and projection are all done through Python programs. And one way of doing this is to say, well, we're never going to label these models that we train. These models are ephemeral. The only relevant thing to them is the data sets that they're derived from. And so we have a pipeline that sort of looks a bit like this. So we take a training set, we do some imputation, we rescale it, we do this training, and that gives us a subspace model. And then we take our sort of a smaller set, and we do the same, and we project the smaller set onto the model, onto the subspace that we've got from the larger one. Which is it's a little bit wider because I want to emphasize the fact that we want to sort of integrate this with Haskell. So actually we connect to a data store, we pull out these data using some ETL process that's in Haskell, and then at the end, after we've taken the projection data, we want to display this in a web GUI. And so one of the things is these subspace models, we really don't want to keep these as like named things. You don't want to have to choose a model to do. Well, that's fine, because you just choose your training set every time. And because we've got sort of sensible caching in there, you choose your training set and it says, yes, I've already got that, I can go up to here. So when you go in, you say, I want to project this small thing onto a model learnt from this large data set. And it shouldn't matter whether we've done the training or not. If we've done it, you get that immediately. If we haven't done it, you get it in a few hours.
Some of these techniques these subspace techniques are randomized. So this is an effect. It's not a pure arrow.
Well, so we would. Well, so one thing is that these aren't necessarily pure, and that's, when you're dealing with external computations, yeah, we can't necessarily guarantee that they are pure, right? They could go and do nefarious stuff, and that's really up to the user to say, well, what do I care about that? Sometimes it could be that I want to not care about that. That's a problem in the underlying library, and actually, I'd just prefer to keep getting the same results I got before. Or you could say, actually, this is an impure step. I want you to explicitly go and rerun this each time. In this case, we were using PCA and TSNE, which are both, I think, stable algorithms that should give you the same results. But yeah.
Yes, TSNE
is it not? Okay.
However, so you can toggle the behavior to be deterministic or not.
Okay. Yeah. Yes.
No, this was a question for your.
Oh yeah, no, yeah. You can toggle whether to have sort of the purity assumed or not. One thing that we haven't implemented, but which we should, is basically a sort of a verification mode which says, I have this product. I want you to run it through again and just check the hashes to check whether it's stable. That just wasn't something that the client in particular cared about that much. Okay, so with the TSNE example, in which case I suspect we were in a case where they didn't particularly care that it was randomized. We've got an example that will do. So this is just a sort of an example of what it ends up looking at. So we've got this arrow syntax, and you take in one data source, which we load from AWS. We load a couple of input sources, and then we run inside Docker, with imputation options, and then scale options. And all of these are running inside containers, so they should be nicely isolated, although unfortunately we have, relied on Docker rather than a wonderful tool from 2013. And then we get the transform output at the end. So yeah, how does this address the original problems? Well, hopefully reasonably directly. So in terms of provenance, I now have an explicit tracked, source of, these are exactly the inputs that came into the system. You know, if I want to walk back, I can walk back through that graph and see this is exactly how this is produced. I can also see, this is how it was produced this time, but it turns out that if I'd done this other thing, I would have got exactly the same results, you know, if I happen to have that in the graph. Reproducibility, again, is kind of a, as you mentioned, it does depend on are your underlying steps pure. You know, there's not really much you can do if your underlying programs, you know, there's not entirely much you can do if your underlying programs are impure and will have sort of random side effects that you can't deal with. You can start to help by, you know, running them in Docker containers and then running them in clean environments, trying to do things like resetting the system clock, etc. But you do basically get a closure over everything that produced this. And if you use things like Docker and Nix as your underlying tool runners, then you basically have everything that came into producing the result in one package closure that you can then ship up and send elsewhere. And isolation, you know, largely comes from the containerized part of it. Although it's also, you know, the fact that you kind of don't want that much isolation because you're not too concerned about because you're you know, you're no longer sort of writing into this shared space. You've kind of got a guarantee that I'm definitely using the same things that I were before. And I'm running out of time, but I just wanted to talk about some sort of potential stuff. So one of the other problems, and actually probably the problem that was most of a problem as opposed to a theoretical, well, we're doing good science, we should have provenance and reproducibility, was it costs a lot of money to do this kind of analysis, you know. Not just the actual processing costs, but when you're storing sort of multiple terabytes of files, they themselves have a cost in storage. And so you really want to address, like, how can we make this as cheap as possible? And this is something that we can actually apply, particularly the storage stuff, a lot to. So, you know, when we're doing this, we can, because we've got this basically what I think of as a garbage collected store, you can track additional metadata like, you know, how much time did it take to produce these items? You know, how big is this item in the store? Like, if I were to delete this, how long would it take for me to go back to, like, the closest products that I do have and recreate it? And by doing this, you can then start to tune up, like, well, I'm short on disk space, so I know that I can let me delete a bunch of things that can be produced quickly, but take up lots of space. Conversely, if I'm short on processing power, I'm just like, yeah, I'll keep everything. And you can also start to do things like, well, even if I delete data, let me retain the link so that I know that, for example, if I take these inputs, I'll get this hash of an output. Because it could be that, well, you know, I start on step A and I walk through to step B, and I'm missing steps C and D. But I know that if I ran steps C and D, I get to E. Oh, and I happen to have E. So actually, you know, why bother even running steps B and C again? I know that I can just run them through in exactly the same way and get to the same place. And other things like, you know, jumping over to other sites and saying, oh, well, you happen to have a copy of this particular hash, so I'll pull that down from you, and then I'll run it here. So, you know, it starts to address some of the other problems about sort of cost models and how can we optimize what we're storing and what we're running. And I think I'm now done with about 2 minutes to spare. Yes, you can email me. I should have put a link to the code, but I can actually do that. Matthew is looking at me like, yeah, what? And you can send me messages on Twitter, but I won't ever read them, so I wouldn't bother. But they told me to put my Twitter handle here, so I have done. OK, any questions? There's nobody to hand out microphones. Just talk loudly.
I'm not entirely familiar with arrows, but they are at the core of your design. Is there any alternative, or what?
I mean, the answer is yes. There are alternatives. You could have written this in sort of, I mean, there's somewhere in between sort of applicatives and monads in power, but you could have written this in another way using sort of monadic computation, and you'd get slightly less because you couldn't actually sort of statically explore the space. I think the answer is there are alternatives, and they're less sort of fundamental to the design as a nice fit that we chose to use. You know, and there might be arguments for using sort of other abstractions around it. So at the moment we use like a free arrow conception, and actually I'm probably going to scrap that, which Tom. So Tom Nielsen wrote the original version of this, and sort of should probably be blamed for everything. And then was sort of highly amused by this free arrow stuff, and I think is now quite gleeful that I'm talking about deleting it. So. Yeah, but the answer is we could have used a number of other things. We just chose to use this.
As far as you're aware, has anyone else done this with the CAS?
So I mean, obviously in build systems, so it sounds like Basil has this. It's a somewhat different.
For these big systems,
Right, there's something called Pachyderm, which somebody linked me to somewhat later, and that potentially has something like this. I haven't looked into it much. There's like a whole load of different ways of going about these, and it's often quite difficult to compare between two systems because, you know, so there are some things that sort of treat the output like a Git repository, and they just have like a massive versioning system on it, which is a sort of somewhat different approach, but ultimately might give you the same kind of results, but in a somewhat different way. So yeah, there's something called Pachyderm that I think might do it. There might be other systems that, and obviously you can use build systems to sort of achieve this. I don't think it's quite a nice fit.
This seems sort of wonderful from a scientific computation point of view, because there's huge problems in doing reproducible research and stuff like that. But it seems like there's quite a big step for your average scientist to get to this, because you have to write this in Haskell.
So you don't actually now,
Okay.
which I didn't include because I was running out of time, but we also have a compiler from, so there's something called Common Workflow Language, which is it's like a sort of YAML-based spec for writing workflows, and that has a graphical editor that you can sort of drag and drop boxes and connect them up, and we now have a compiler from that into work. And actually, in some ways, that's better because one of the I can't answer this question, but I can talk to you afterwards. Okay, thank you very much, people. Right, I can just unplug.